Hello everyone, my name is Natalino, and in this video I will show to you our demo to the OFC 2023 demo zone. The title of the demo is Scalable and Efficient Pipeline for Machine Learning Based Optical Network Monitoring. I would like also to acknowledge and to thank my colleagues from Chalmers and CTTC who together have been working with me in this demo and also in the context of the TeraFlowSDN controller. So nowadays, software-defined networking and machine learning are two of the main enablers for disaggregated operation of optical networks. And in particular, when you disaggregate optical networks, you want to also have in place closed-loop automation processes that are able to help you manage this disaggregated infrastructure. The closed-loop automation and the consequent autonomous operation that closed-loop automation brings enables you to have lower safety margins in your optical channels, but it also comes with a more stringent requirements in terms of reaction to potential service degradation or malfunction equipment. So in this context, the collection and the diagnose of optical channels scale with the number of services in the network. So having a pipeline that can automatically scale together with this number of optical services is crucial in order to maintain or to retain the benefits of closed loop automation. So in this context, our demo showcases a scalable, efficient, and flexible diagnosis module for optical networks. The demo is implemented using the ETSI TeraFlowSDN, that is an open source cloud native SDN controller. The demo scripts are also available open source, but we believe that the module and the strategy can be integrated into any SDN controller that you might want to. So let's have a better look at the collect, diagnose, and act loop. So in this case, what we have here is in the collect stage, the SDN controller or your monitoring and or telemetry software collects the data from the devices and consolidates them in a database where you are able to take advantage of it by running the diagnosis step. That is where we can use theoretical models or we can use machine learning models in order to obtain or to get more information from the data collected. So for instance, we can run here anomaly detection, we can run here in the diagnose the quality of transmission estimation, quality of transmission prediction. We can also have here physical layer attack detection and several different kinds of algorithms may be running in this diagnosis step with the objective of making sense of the collected data and giving input to the act step. That is the step where you make changes to your infrastructure. So this step is triggered whenever the diagnose module detects that some change or some update is needed in your network. But the act is also triggered when you have new services in your network. As you can see here, there is a crucial difference between these three steps, that is how they scale with your infrastructure. In the case of the act step, it scales with the services changes. So this means that you only trigger this step whenever a change needs to be made in the network. However, if we look at the collect and diagnose steps, these scale with the number of deployed services. So each new service that you deploy in your network will need or will trigger procedures in these two steps. And these procedures are periodical. They are repeated in a given period. Therefore, scalability is a critical aspect of it. So in terms of the collection of data, this has been addressed in the literature by concepts such as network telemetry that studies how we can more efficiently, more effectively get the data from the devices into a monitoring database where then the diagnose module can act on that data. However, in the case of the diagnosis step, in the literature, the scalability properties have not been fully studied yet. So there is a need here for scalable pipelines that are able to handle any amount of data that comes from the collection step in order to give to the act step appropriate and timely decisions. The problem that we want to solve here in this diagnosis when it comes to scalability is given the desired loop time, so let's say that we want to execute this diagnose every 1 minute, every 30 seconds, we need to scale the resources accordingly such that the desired loop time is met. So in order to do this, we proposed a module, and this module is here represented in the context of the ETSI TeraFlowSDN, but again, the module can also be deployed in a standalone fashion. And this module is composed by 4 main new components in addition to a cache, where we can use any standalone cache. But besides the entirety of the SDN controller, what we have is 4 different modules. The first one we call OPM Manager, and this is the component that is responsible for managing the entire loop. So it's the one that triggers everything. Then we have the Optical Service Monitor, and as the name implies, this will do the service monitoring in the for each one of the services independently. And it will take advantage of the attack inference, that is where we have machine learning models able to perform the inference based on the data obtained by the service monitor. And finally, whenever any anomaly is detected, we have also the mitigator that implements algorithms that should be able to mitigate the anomaly detected or the failure or the attack detected, making this attack mitigator be the part of the act in the entire loop. This control plane is deployed, and through the southbound interface, it talks to an open or an optical line system that manages an optical network. So this is the context, and then we can analyze more closely the communication among these different components. So the OPM manager is it has a unique structure here because it is the only component here that does not scale in terms of replicas. However, in order to make this a reliable component, what we established was an initialization procedure that allows it to start at any point in the network operation. So if the component for some reason crashes, or if you want to deploy this module in a system that is already functioning, there will be no problem because the OPM manager during the initialization phase already talks to your SDN controller core and gets the current list of services. Then, during the operation, the OPM manager also connects with your SDN controller core in order to get service events. These are notifications whenever new services are created or existing services are deleted. And this allows the OPM manager, these 2 procedures, the initialization and the service setup, allow the manager to maintain an updated list of the current optical services running in your SDN controller. Periodically, in a different process, there will also be what we are calling here the OPM loop that basically is the one that executes the diagnose step. So in this loop, what we have is that for each existing optical service, the OPM manager delegates to the service monitor the monitoring of each one of these services. Then the service monitor, if is using an unsupervised learning inference, obtains a window of samples from the cache in order to not overload the monitoring component of your SDN controller with too many requests. So we have a cache here that is local and temporal also, but it also gets the latest data from the monitoring component. So by doing these two different calls, what we have is that the monitoring component will need to reply only with the latest data that was not seen by the service monitor before. Then the service monitor calls a machine learning inference module in order to get an inference on the data that was gathered before. And if an anomaly is detected, it will also call the mitigator in order to mitigate that anomaly. The service monitor also includes the result of the inference in the monitoring database using the same timestamps as the samples in the monitoring, such that it also enables you to visualize the results of the inference together with the monitoring data that was used to get it. And then the service monitor closes and finishes processing the service. And of course, this process is repeated for each one of the services. So in this case, there are several processes going on. I would like to mention only one very important case, that is how this periodical loop is implemented from the perspective of the OPM manager. So we have here the pseudocode, and I will go quickly through the steps, but the periodical loop receives the current list of services, the period that it should repeat, and it gets also a client to the monitoring component of your SDN controller core. So the periodical loop is a singleton, meaning there are no replicas, but in order to cope with a large number of optical services, we use a multi-thread approach. We have a minimum number of thresholds, and then we enter the loop, where we initialize the tasks and we get the beginning of the loop execution, and then we enter into the loop where we delegate to the monitor the monitoring of each one of the services, and this is done through creating async tasks. So these tasks are combined into a list, and then we create a thread pool where we run this list of tasks using the thread pool. So we distribute over multiple threads the load. Once this is done, we take the elapsed time, we report this, and we compute the result, or we compute the number of threads based on whether or not we matched or we were able to match the elapsed time with respect to the period. So if the elapsed time was greater than the period, we already start the next one immediately. Otherwise, we sleep the process for some time. This pool is executed in a very unique fashion, where we create a thread pool that has a number of threads, and then each one of these threads will execute concurrently requests to the monitor. So each request will be specific for one given service, but they are done concurrently. We are able to send all these requests in a concurrent way, and then we just need to await for all of them to finish. Once they are all finished, we are sure that the loop is finished. So this allows us to scale even though we are not using multiple replicas. So in this demo, I will show you later the result of the deployment, where we have TeraFlowSDN, we have the components that we implemented, and we also have a Prometheus collector connected to a Grafana dashboard. And in terms of data, we have recorded different metrics, and this recorded data set is used by an emulated optical network and an emulated optical line system in order to receive and send monitoring data. So all the data that you see has been recorded in a real testbed, but we are reproducing it for the sake of the experiment. So now let's go to the live demonstration. Some parts of this live demonstration will be sped up so that we can have a more clear vision of the dynamics. But as you can already see, we have this dashboard So we have here, starting from the left top part, the number of optical services. Currently we have 0 optical services in our network. We also have here in the loop time both the desired and the measured. As you can see here, the desired is currently 30 seconds and the measured is close or below 1 second. Then we have the number of workers. So this is the number of threads that we have in our OPM manager. And we also have a measurement of the response times of each individual component, the service monitor, the machine learning inference, and the cache. So this response time refers to the response time for each service that is being monitored. We are also monitoring here the resource consumption in 2 different plots. The first one is in terms of number of replicas. So currently we have the minimum number of replicas, that is 2 for both the service monitor and the machine learning inference, that are the 2 components that scale in terms of increasing the number of replicas. And we also have the total CPU utilization for each one of these components. So this is a stacked plot. So this means that what we are seeing here, the green line is the consumption of the manager, then the yellow line is the sum of manager plus the service monitor, and also the blue area represents the resource consumption of the machine learning inference. I will start by increasing the number of services to 10, just so that we see how the dynamic works. So I'm now just inserting 10 services in the system. And as you can see, the 10 services were added to the network. So now we can see that we start to have some dynamics happening. For instance, the response time, now we can see that we start having some measurements of response time. And of course, there is nothing substantial happening in the resource consumption because we only added 10 services. Now, what I will do is that I will insert 90 more services, so we should have 100 services in total. As you can see, the 100 services are already in the system. You can see that the measured loop time already increased, so it went from less than 1 second before with 10 services to now 7 seconds. We can also see the response time dynamics here, so there was not a big variation. And as you can see, there is a further increase here because now we are getting the latest data from the 100 services. So now what we will do is that we will increase the number of services to 500 so that we can start seeing some more dynamics in terms of scalability. As you can see, here we had an event where upon inserting 500 services, in the first execution of the loop time, the measured loop time, was above the one that we desire. So in this case, what we had is that the OPM manager increased the number of workers from 2 to 3 in order to cope with this. And we can also see in terms of replicas, service monitor and machine learning inference spawned new replicas in order to cope with this greater load. So what we can see here is that the system now is going through a transient where the number of workers and the number of replicas will be varying in order for the system to bring the loop time below the desired. So I will now leave you with some of these dynamics until the system stabilizes. After a few minutes, what we can see is that the number of workers in the OPM manager went back from 3 to 2, and that is because the number of replicas of both the machine learning inference and the service monitor went up. So now they are able to process more concurrent requests. So the OPM manager is able to scale down back to 2 threads in order to get it done. And we can even observe that at some point the number of replicas may also be reduced here, since the load is not increasing, because we are still able to maintain a quite stable loop time. So now I will progressively increase the number of services until we reach 1000 services. We can observe here that when we increase the number of services by 100, there is a violation that spans for 2 minutes of the desired loop time, but that is just by 2.5 seconds, and after 2 minutes, due to the scaling in the number of workers of the OPM manager, we have a substantial drop where the loop time goes back again below the desired loop time. Well, what we can see here is that when we progressively increase the number of optical services, and this is a more realistic scenario because you will get only a few, maybe a few tens of new services every 5 to 10 minutes. And when this happens gradually, what you can see is that there is no violation in the loop time. There is enough time for the system to stabilize. So here we got very close to the desired loop time. But as you can see, the number of workers and the number of replicas is scaled in order to maintain the measured loop time below the desired one. Another thing it's worth noting is that the response time remains quite stable. So if I put here the last 15 minutes, what you can see is that even though we had great variations in the number of services and in the response time in terms of loop time, the response time of the components was kept relatively stable. So this means that the system is able to adapt and to maintain operational conditions in various conditions. So a final test that we will do is we will change the desired loop time from 30 to 60 seconds, and we will observe how the system reacts and how the system adjusts the resources allocated to it. As you can see, since we increased desired loop time, what we had was an adjustment in the number of workers down from 4 to 2, and after this, there was also a consequent reduction in the number of replicas necessary for the service monitor and the machine learning inference. So this means that as you find the correct desired loop time, our solution is able to scale, either scale up or scale down in order to meet the desired loop time, but at the same time, in order to use as little resources as possible. Well, just to conclude, the proposed architecture, as you could see, scales all the resources to different degrees in order to adapt the number of services being monitored, given the desired monitoring period. The efficiency part is demonstrated by dynamically adjusted the amount of committed resources. So this basically means that we only commit resources when we create new replicas, and we only create these new replicas when there is enough load. And the flexibility is illustrated by using different machine learning models. So to conclude, I would like to thank all the partners of the TeraFlow H2020 project, and thank you for your attention. And I would be happy to answer any questions you may have. You can contact us through our social networks, or if you are attending the conference, you can also use the conference chat for that. So thank you very much for your attention, and have a nice one. Bye bye.